So now for this part, I'm going to give just a short presentation as an application to give students an idea on how to present their works. So first of all, I would like to introduce myself. Assalamu alaikum. This is Naziha Belmahi from the University of Science and Technology, Oran, Mohammed Boudiaf. This presentation is entitled Stability and Hop Bifurcation for the Glycolysis Model Involving Caputo Fractional Derivative. So this presentation is divided on the following parts, where we start by a brief introduction, then we state the main results on stability and hop bifurcation. After that, there is a part of the numerical simulations to validate the theoretical results, and we end by a conclusion. So to start with, we give talk about the glycolysis phenomena, which is a very complex process by which living organisms extract energy from the glucose. So this process is a fundamental step for the sustainment of life. And the sustained oscillations were and are being observed in glycolysis by various settings. That's why in 1964, Huygens used a mathematical model to have a better understanding for this phenomena. But later, in 1968, Silkov observed that Huygens did not show the sustained oscillation for biologically correct parameter values. And thus, he proposed a new model, which is referred to Silkov model, and it is presented in one. In this short paragraph, we focus on the main characteristic of using fractional derivative instead of the integer order derivative in the modeling of real-life phenomena with memory effect, since this derivative is non-local. Thus, by involving the Caputo fractional derivative, we introduce a new model which is presented in two. In this slide, we present the main results on the stability of the proposed model 2. 1,1 is the equilibrium point of this system, and it is asymptotically stable if one of the following two conditions is satisfied. So, the first condition is obtained by using the fundamental theorem of stability, which says that E is asymptotically stable if and only if the determinant of the Jacobian matrix is positive and the trace is negative. And this condition is a stability condition for both of the integer and the fractional order systems. However, the second condition is obtained by using the theorem of stability for the fractional order systems, which says that the argument of the eigenvalues of the Jacobian matrix is greater than alpha pi over 2. It is clear that the first condition is independent of alpha, which means that the region obtained by this condition is stability region for both integer and fractional order system, and it is noted by I1. However, for the second condition, we obtain the region noted I2, which is stability region for the fractional order system. However, the integer order loses stability. So here, as you can see, we plot the alpha-gamma bifurcation diagram for the system 2 for A equals 5. As you can see, I1 is the stability region for the fractional and the corresponding integer order system. I2 is the stability region of the fractional order system. However, I3 is the instability region. In this slide, we analyze the hop bifurcation existence. After some computations, we get that gamma bar, which were noted in the previous slide, is a hop bifurcation curve. Now, we pass to the most important section, where we present some numerical simulations that we performed to show the advantage of using fractional order derivative instead of the integer order derivative on the dynamics of the system. The parameters are chosen in the regions I1, I2, and I3. For this figure, we choose the parameters in the region I1 and we fix alpha equals 1. So we are talking about the corresponding integer order system. As you can see, E is asymptotically stable. And for this one, we keep the same parameter values. However, we take alpha equals 0.89. So E is also asymptotically stable for the fractional order system. This figure is obtained by choosing the parameters in the region I2 and alpha equals 1. As you can see, E loses the stability for the integer order system. However, it is still stable for the fractional order system. In the following last figure, the parameters are chosen in I3, and we remark that E loses the stability for the fractional order system and a limit cycle occurs. So we end by the conclusion that the expansion of the stability region is one of the main characteristics of using the fractional derivative on the dynamics of fractional order systems. Here we present some references that we used in the validation of our work, and thank you for your attention.